Good evening, everyone. Welcome to ninth live session for the course Functional and Conceptual Design from IIT Madras. My name is Neelarnab Dutta. I'm a PhD scholar and a PMRF fellow from IIT Guwahati. In this particular lecture, I'll be covering important concepts from week 9 lectures. So, have you gone through week 9 lecture videos? The deadline for assignments is tomorrow. Yes. So, have you gone through week 9 lecture videos? Okay, so deadline is tomorrow. So if you have not finished your assignments yet, please finish them on time. Since the nature of the assignments are objectives, so this session will be more conceptual. I'll try to clarify some of your doubts, which will help you in solving those assignments. Okay. So this is what we learned in the last week. Okay. And in the last week, we learned about various types of product architectures, okay, mainly portfolio architecture, which represent a family of products. Okay, so basically, there are three types of product architectures. One is fixed unshared. So within fixed unshared, we discussed about single offer and robust offer. Okay, similarly, there are modular portfolio architecture, which can be modular family architecture, modular family, then modular generation, and then we have the consumable, okay, standards, and parametric. Similarly, the another type of portfolio architecture is customizable, which also have two subcategories. One is bespoke, which means you are customizing something for the user at the time of manufacturing, and the another type is parametric, where you are designing something that fits different customers. So there are some sort of adjustable or parameter which you can adjust uh, at the time of use. Okay. Okay, then we learned about how to choose a portfolio architecture. So for that, we first need to gather the need, okay, user need, and then we need to rank them accordingly based on those needs. So if there are three needs, then we try to rank them with some number, four, five, four, five being the highest importance. And then we gather various statistical informations. Okay, statistical informations like population, mean of a need value. So every need needs to be converted into a specification. So specification will have a matrix and a value, right? So basically, we are trying to identify the population average of that particular need value. Okay, and then we try to identify various categories within the population. So there can be different population segment, like like male, female, can be elderly. Okay, so based on that, we again identify individual mean for each of these segments, and also the standard deviations. So how much population deviation occur within that particular parameter. So this is population uh, standard deviation, which is denoted by sigma. and the others also can be represented by sigma 1, 2, 3, like that. Okay, so and after collecting all this statistical information, we use some sort of flow chart to identify which sort of portfolio architecture we need to consider. For example, if a population mean is fixed with respect to time, that means a particular need value does not change, okay, over time. So this is like 2008, and in 2020 also the need remain the same. Okay, so if you find that the population mean does not change, okay, it's remain the same, then you go for a next checkup. But if you find that there's a change in the mean value over time, then you go for modular generation architecture. That means within a product, for example a camera, the desire for a lens optical zoom can vary. Okay, so in 2008, if the lens size is like, if you using a lens you can do 2x zoom, in 2020 probably you need a 4x zoom. Okay, so this is what is called generation platform. Similarly, after identifying that the mean does not change, then you can go for the next thing, which is the population sigma large. Okay, population sigma large means population standard deviation large. That means we have a very wide bell curve. That means there are a lot of variation, okay, in value that people demand. Okay, so a more wide distribution means there are a lot of variation that people are looking for a particular need or specification value. That means if it is yes, then we'll go for next, but if it is no, that means the population sigma is not large, it is very less, that means it is very narrow. Okay, then what we can go for, we can go for fixed unshared portfolio, for example like a screwdriver. Okay, where we do not have to think about various user, we can just produce one standard tool with a standard head, because the requirement for a particular size or shape of this head is fixed for all. For example, if it is M8 screwdriver, across the population, the shape of, or the value of this length will remain 8 mm, with some plus minus very minute deviation, standard deviation. So again, similarly, if you find that population sigma is uh, large, okay, that means lot of variation, then you go for segment. You try to compare with the segment values. So if your individual customer segments like male, female, okay, and if their standard deviations are same as the population. For example, if this segment standard deviation have the similar width, that means what? That means we need to have something adjustable portfolio architecture, because in order to capture each of this segment, we cannot come up with one precise fixed and shared portfolio architecture. We need to make it a adjustable architecture with a provision to make it adjustable for all the segments. So we need to choose something like this. Okay, similarly, if the population mean is not, population standard deviation is not as wide as, sorry, the segment standard deviation is not as wide as population standard deviation, then we can go for modular product family. That means for a male person we can have a different product, for a female user we can have a different product. So this is what is called modular product family. Okay, clear?
Yeah, it's clear. Thank you.
Okay. So this was what we learned in the last class, and which was about product portfolio architecture, which is basically defining the architecture for the entire product family. Okay. In today's, I'll be discussing about for a particular product architecture. So this means an architecture defined for an individual product. Okay. So what does a product architecture means? Is basically the scheme by which the functional elements, which is important, functional elements of a product are arranged or assigned into physical blocks. So if you attend my week 7 lecture videos, I have discussed about a sachet dispenser, and I tried to explain like how there are different units, modular units exist within that particular sachet dispenser. So this is what we mean by product architecture. That is how we can convert various functional elements into physical blocks. Okay. So the key considerations we need to take are how product a product offered variety. Okay, that is like while trying to define a product architecture, we need to consider the variation among the product. Okay, and then we also need to think about when we are trying to break down a particular product functionalities and then try to group them into specific modules. Are we going to increase the product cost? Okay, which is the best possible way of grouping functionalities so that we can have a reduced cost. Then again we need to consider like design lead time, like what is the what will be the time requirement if we try to integrate two different functionalities into one unit. Okay, to make it a physical different physical block. Okay, so all the development time period may suffer if you make a wrong decisions. Okay, instead of pairing or choosing some different modules, you end up choosing something else, then probably it will increase your development and design timeline. Second thing is the fourth thing is like development process management. Like if you are trying to do some sort of product architecture design, you need to also consider at the end, you need to actually physically make that particular product. So how you will be doing that, so what sort of skill sets you will be requiring. Okay, and will which particular module you will be outsourcing or which you will be manufacturing in house. So all those decisions needs to be considered while doing product architecture. Okay, clear? Any question?
Development process management, I didn't get. Can you repeat again?
Okay.
Sorry.
Okay, so for example, you have a particular, uh, let's take an example, like a juice machine, okay, juicer, okay,
Mhm.
and we have a below the electrical unit, and we have a jar unit on the top. Okay, let's take only these two part, or let's, and there are also inside there is a power unit. Okay, and there is a another is a rotary unit which will convert the electrical power into rotational motion. Okay. Now you can divide this into three modules. Okay, one way is like one, two, three, right? One is like, okay, one, the conversion of 220 volt into something 12 volt, that particular electronic circuitry will be one module. Okay, and then
Mhm.
12 volt electrical energy to this rotary rotational motion to produce that particular torque is another module. Then particular this blade assembly may be a fourth module, and this particular glass is a first module. Okay, now there's a way. Okay, like if you have to do this, you need to uh, you need to plan your development process in such a way that you send this particular unit for someone who is good at plastic injection molding. You are sending the blade assembly to someone who is experienced in designing or manufacturing blade assembly. Then similarly electronics you will send to someone who can produce electronics. Okay, now think this way, like if you try to combine one and two into one particular module, okay, what will happen? It will hamper your overall development process, because now you will have a jar with a fixed blade assembly. Okay, that means the blade assembly is a part of the jar. So you need to plan accordingly, for making those design decisions. So you need to change your development process. You need to manage them, okay, differently. Understood?
Yeah, yeah, I got it. So basically, you are saying, if you wanted to change certain, function, if you want to combine the function of two, which you are dependent on to a stakeholder. So
Yes.
then you have to manage your time and before doing the development, correct?
Yes, one is third one is the time thing. This one is like
Mm.
how to manage resources, like human resources, like your if you're a big company, you will have different sub departments. Like there are industrial designers, there are mechanical designers, there are some workshop guys, there are someone who is working in electronic. So you if you send something like this, which is having a metal component and a plastic injection molding parts, and
Mhm.
send them to manufacture this as a one unit, what will happen? These two group, one is who is handling plastic injection molding, the another who is handling blade assembly, they needs to work together to come up with this particular solutions. So you need to
Yeah,
manage
correct.
your development process. Okay, otherwise
Okay,
if you make it a serial the other way, like if you make it different, this is different, then this is like a standard, you can easily do it at your end. Okay, so
correct. Thank you.
products can pass like this. Okay. So, okay, so within the product architecture, we have two different types of product architecture. One is integral architecture, and the another one is modular architecture. Okay, so do you know what is integral architecture and what is modular architecture?
Yeah, integral architecture is something like it's a like physical form which has two three function, but it's like combined together. We cannot separate, and there is no integrated relationship between three function.
Okay,
So that's what like here you can see the screw, right? A screw driver. So we have two three function, like two three element is there, but there is no integration of relationship of
oh,
function.
okay,
But other way, like modular architecture, when I say that, so there is a model, there is a screw which is an adjustable jaw, which I can see. So that is modular, and that is kind of you can remove, and it has different function also.
okay, right. So basically, in integral architecture, you may have one functional block or more than functional block, but those are not physically separable. Okay, and the relationship between each of these elements are not well defined, they're ill defined. And all these components, although it has a plastic handle, a metal screwdriver, all those elements are intended to do only one primary job, which is screwing. Okay, but in modular architecture you have physically separable functional blocks. For example, here you have a jaw, a screw, and a metal body and plastic these things, and these have well defined functional interactions. That means when you rotate this particular thing moves. So the relationship is active. Okay, so active interaction. This is more like a passive interaction. That means this is just like a grip. There is no mechanical relative motion between these two components. It's act only as a grip. So instead of holding this particular metal body, you are holding this just for ergonomic purpose, but they are serving just one particular purpose. Here also, you have this is again one grip only, so this falls under integral architecture. However, there's a screw. When you change this actively, it interact with, it changes the the distance between these two jaws. Okay, that's why it's called a modular architectures. Now there are few factors that you need to consider, while designing modular architecture. So that you can consider those as like the factors that affects a modular architecture. One is product changes. That means you need to provide a scope, okay, for product changes. Basically, you are trying to provide future scope for making certain changes. For example, probably a component inside your product may get spoiled or get damaged. So in that case, it should be easy to change that particular feature or function. So product changes. Similarly, product varieties. So with modularity, you should be able to actually achieve a family of products. So probably one particular product, it's more like a modular family, okay, and the another particular product have the same assembly, but one have a one is wired, the other one is wireless, okay, but they share almost the similar modules, okay, just one extra part this comes. So this enable product varieties. Then component standardization. So there can be few components which are standards which needs to be used as a standard component, so those also needs to be considered in product architecture design. For example, if your design needs a LCD and this is available as a standard component, you need to use this standard component. You do not have to actually go for integrating a LCD and a new speaker system and try to create one module. If something is available as a standard, use it as a standard. Okay. Similarly, you should also consider product performance. That means when you are integrating, does it affect the product performance? Does it enhancing the product performance, or does it degrading the product performance? Those things needs to be considered. Fifth is like manufacturability. When you are integrating, like in the last example I gave, when you come up with some design having a plastic body and a metal blade, what will happen? The manufacturability will be difficult because it is easy to manufacture this plastic ball using injection molding. There can be like dyes, okay, molds, and then you can actually get that part out, then later you can assemble the blades. That is easier. However, if you try to integrate both together, it is difficult to manufacture. So those things you need to consider. Again, product development management I already discussed. Like when you are integrating something, it will affect your overall development planning. Okay, any doubt here?
No, no, thank you. Yeah, everything is good.
Okay, so here's a quiz. So class quiz for you. Okay, so can you tell the product architecture for the following products? Say plier.
It's a modular architecture.
Why?
Uh, Modular architecture. Um, I have doubt because it has, I think, certain some assembly system like
Okay.
on basis of this it jaw expand and shrinks.
Okay, so
So that
remember this, in integral, okay, you may have multiple components. Okay, see there is one component, there is two component, there is this is three, this is four. But if you separate these, this will not act as a plier or cutter. Okay,
Mhm.
so the overall functionality the will exist only with the integration of all these four elements: one, two, three, four. So this is a integrated architecture, integral architecture. Understood?
Okay, yeah, okay, fine.
If see, imagine last time you gave the example for the spanner. What happened in the spanner? Even if you remove this particular screw in the middle,
Hmm.
still these jaws can be moved. Okay, this is just the additional mechanical advantage you are putting to make this thing, semi-automatic or easy for you.
Okay,
Okay,
okay.
however, here what happened, there's without, see, only this thing will not work, right?
Mm-hmm.
Only having this part or having this below part,
It
no.
has to come together.
Yes, it has to come together. Then only it will serve this one particular purpose. It has only one particular purpose, that is cutting. That's why it's an integral design. Does not depend upon how many different elements exist. Okay, if
Mhm.
they all are intended to make only one particular function, it is an integral design. Okay, next, juicer. So what do you think?
Modular, it's obvious.
Modular.
Modular.
Okay, because we have a electrical unit, we have a plastic things, and all of this will, can be physically separated and can be manufactured functionally. They have different purposes. That's why those are modular. What about
Yeah.
nail cutter?
A nail cutter, it's a, I think, integral product, but there is some, yeah, integral product.
Okay, that's, I gave purposely this particular example because in the live class,
Hmm.
what Professor Asokan has explained is about a nail cutter, which is only the cutter part. Okay, it is like this, something like this, and having the top. Okay,
Okay.
here if you see, you have, you know other things also. Okay, so what is the purpose of this? This is to hold, right? To, hang or make a key ring. Okay, this can be removable, physically separable. It has a different function. This particular unit is a
As
one integral part for cutting. It is not physically separable. If you remove one of these, element, it will not work as a cutter. This is again for cutting some, fruits. Maybe this is for probably scraping your nails probably. So,
the,
it has multiple entities which have different functions, and those can be separable. That's why it's a modular architecture.
mod,
But if you give an example where there's only the nail cutter portion,
this needs to,
it's
it's,
a,
it is an integral. Okay.
yes, yes. Okay,
Mhm.
what about this one, fighter jet?
Oh, this is modular.
Okay, okay, so what we learned so far is like product architecture can be divided into integral architecture and modular architecture. But again, modular architecture can be also subdivided into two categories. One is manufacturing based modularity and another is functional based modularity. So manufacturing based modularity means based on manufacturing techniques and assembly operation, you are actually, uh, grouping the components. Understood?
Yeah, yeah, correct.
For example, if this is a helmet design, if you see this particular portion is a transparent, windshield. Okay, so that means you need to use some different manufacturing process to come up with this transparency, and the rest of the, helmet can be manufactured by some other process. So based on the manufacturing technique, we are just differentiating or, breaking down this particular product into two part categories. Okay, one is this black part, one is the transparent portion. So this is how we are defining product modules based on manufacturing practice. The another, way how you can break down, or one how you can create modules is based on their functions, product functions. So these are based on basically mainly how, uh, various products functionalities and how these functionalities are, integrated or connected with one another. So based on that, actually we have the function based modularity. Okay, so there are again four types of function based modularity. One is slot modularity. Do you know what is slot modularity?
No, no, I think I don't know. No, I don't know.
Okay, okay, there are four types of function based modularity: slot modularity and bus modularity. So these to have something similar, that means there is a some sort of base platform, and you have for slot modularity you have some sort of physical slots. Okay. Okay, so this is
Mhm.
a base module. Okay, and in these slots you connect, different modules for your product. So this type of modular design is called slot modularity. For
Okay.
example, if you see the mixer grinder, okay, so the top part where there's a slot and a mixer jar actually fits, different mixer jar also get fit into that particular slot. So this is slot modularity. Got it?
Yeah, yeah, good.
Bus modularity is something where we have a base platform, but the shape of the particular slot is the same. So in slot modularity, it is not required that in a particular product all the slots needs to be of the same size shape. Okay. However, in bus modularity, we call it bus modularity when the slots are of similar shape. For example, if you consider a PC and you use the, if you see a old PC where we used to have some sort of cable, okay, and that particular cable actually can be fit inside, that's a SATA cable. It can go to a SATA hard disk, it can go to a CD drive. Okay, so this is some sort of bus modularity. Okay, similarly in the bike assembly, if you see the how the headlight connectors, they have these four pins. Okay, and there are multiple of that, multiple of those connectors. For example, for DRL one is there, for main central, low beam, high beam, you have different, but for all of them they use the similar shape of the, slots. So this is again bus modularity. Okay, sectional modularity is where there is no base platform. We use different sections. Okay, and then we sections can be of any shape actually, and then we group them to create some sort of some structure which provide a bigger functionality. Okay, those can be, like a chain. A chain can be a sectional modularity. A cubicles in a office can be sectional modularity. You have the same uh, rectangular pieces which you can actually arrange to create different, designs. Okay, so these are sectional modularity. The third type is mixed modularity, where basically we have a combination of all these three. Okay, generally this is, if you see a complex product, something like a Lego, device, Lego based product, or something like a aircraft, complex product having, different, both bus modularity, slot modularity, and sectional modularity. So basically computer PC probably will represent a mixed modular design. Clear?
Yeah, yeah. Okay.
Okay, so next question is like what we learned so far is like, what are different types of, modular architecture, but how to decide, uh, how to come up with a particular module structure, like how to group functions. So have you gone through the lecture slides of week 9?
No, this time I have not gone through entire thing. Only
Okay,
half have gone.
okay. So basically there are two techniques which we can use to define particular module. Okay, for example, if we have a lot of functions. Okay. Now the questions is how to group these. Okay. What is the best way this can be grouped to come up with some modules? Okay. So for that, okay, there can be like two modules, there can be three modules. So for that, we use two basic techniques. One is called basic clustering method, okay, and the another is called module heuristics. Basic clustering method use a simple approach like what we what we experienced in the last two lectures of creating a function structure. Okay, so we have a flow model, right? So from flow model we create a function structure. So based on the function structure we can come up with we can cluster various functionalities to come up with certain modules. In case of module heuristics, we use some sort of heuristics, that means rules, some set of rules or guidelines we use to combine or group different functionalities. Okay, so let's keep me first start with basic clustering method. So in basic clustering method, what we do is we first create a function structure. Okay, so do you
Okay.
remember what is function structure?
Function structure, like it's
So
a, yeah, like generally function structure be input and output in between. We get to know, there is a tree structure or function tree structure.
okay.
Based on that, I think flow model of the function structure can be created.
Okay. So initially we learned about some simple techniques, okay, which can be easily uh, used to make simple products. Then comes the complex products where actually there needs a more robust method. So there we use a flow model. So flow model basically have certain input flows, okay, flow of energy, flow of material, and flow of information or signal, and
Yeah.
there is
Yeah.
again outcome is energy, material, and you have signal, info or
Signal.
signal, and in between we try to establish the various functionalities, how this particular energy get transformed into the output energy. Similarly, how input material can be converted into output material using certain functionalities, and while doing that we also realize some sort of interrelationship between uh, information, material, and energy. Okay, so we end up something like not a tree structure but something more complex than a tree, having multiple relationship with. So we do not call this as a tree structure, we call it a function structure.
Function structure.
In case of simple products like a electric saver, we have only simple one particular critical function path. That's why those can be easily represented as a tree structure. For example, for electric saver, we can just say like, okay, this needs only one particular hierarchy because converting electrical energy to dc voltage to trim to
Always and also there.
then finally cutting, so it can be represented using a simple tree structures. But
Okay.
in case of complex product we use flow model and then we come up with a function structure. Okay, so what happened, like after we come up with a function structure, then we try to cluster various elements, okay, based on how they are related, okay, uh, like how they establish the relationship with respect to the input and output flow. Okay, so let me explain. So for example, you will combine these three if this is three functions you are trying to combine it one, probably they are sharing common energy. Okay, if you are combining these four, okay, probably they are sharing common material. Okay, in case of a, what happened in case of a sachet dispenser, you know, sachet goes inside and then at the end it cuts into specific, pieces of sachets. So they are, material, it is the modules, different modules sharing the same material, the sachets. That's why you are grouping them into one unit. Probably another can be the signal. Okay, probably for various signaling you are using one particular LCD. That's why those can be combined in as a one unit. You are doing signaling for different modules. Okay, so depending upon the relationship that you can see how they share these inputs. Okay, these three types of inputs, you try to group them into individuals, categories and modules. Okay, after that what you do, you go for a rough geometric layout. Okay, however, while doing this at this stage 2, you need to also consider the future technology. For example, a particular technology is soon going to come, you know that, and you need to change that particular technology for future use. So you cannot group that particular technology within a set of other technologies. It will be difficult for you to manage that in a product pipeline. Got it?
Yeah.
Okay, so where I was like, uh, so there was some sort of internet connection issue this
So
side.
we were discussing about how to group the function based on their
Yes.
function and
Okay. So this,
input.
okay, so we need to come up with a rough geometrical layout, okay, based on our groupings, where we will try to create some sort of physical form. Okay, so we're trying to create some sort of physical form and try to establish how this physical entities will be connected, how, what sort of like as I discussed, what sort of modularity we will be requiring. If we need slot modularity, we will be looking for some sort of slot and bus modularity. If we think of something like a sectional or mixed modularity, we need to think it accordingly. Now the decision what needs to be chosen is based on your experience and how various standard connections and modular attachments are available. Okay, so next phase is like
It will
defining the.
also depends on product, right?
Yes, if you are
Like suppose
designing
we are going to design furniture, no, but it will go up to sectional modular only because different pieces will be manufactured and then you can assemble it.
Yes, okay. If it is a furniture, then it will be a sectional module. So you can have something like a plastic. So a lot of nowadays Neelkaman's plastic furnitures are come as this kind of slot modularity architecture in that form. So they have plastic tubes, and then there are some sort of joining joints, and again you connect another rod, and at the end you end up creating some sort of
Hmm.
wardrobe, okay, with some sort of doors. So those are again a slot modular architecture. Okay, so
Based
after.
on product demand, but your thought based on that we have to take the decision, which is
Yes,
feasible.
yes, so we
Okay.
need to come up with some sort of three-dimensional physical block. Okay, and then we need to think how these can be connected. So we need to check for standards, first standards. If standards are not available, then we go for custom. Okay,
Okay.
and
Yeah.
then next thing is what we do, we try to check various interactions which can hamper the particular performance. For example, if for example if it's a electrical device or electronic device, there can be some unit which can actually generate some sort of heat energy. So you need to make sure when you are connecting this particular module with some other module, there should be some sort of heat shield. Okay, so all these four elements, or sorry, three inputs: energy, material, and information. So you need to recheck if there are additional requirements for the kind of interactions we are getting when we are designing a particular product. Okay, so when you are probably connecting uh, two modules, okay, there can be like electrical safety that also you need to provide. Maybe you need to provide some sort of insulation. Okay, so electrical insulation and heat energy all falls under energy. Okay, similarly, if you have some components which are dealing with some sort of liquid, okay, for example, in a
Okay.
mixie grinder you have some sort of liquid, okay, then there's a electrical section in the below. So these two
Yeah.
modules should be connected in such a way that the material does not spill over. Okay, so similarly
Mhm.
you need to also consider how, material also should not go between different modules. Okay, so depending upon like the kind of effects that can create, okay, ill effects that can create in terms of energy, material, or information, you need to also check for, how you can isolate individual modules. Okay, so this is the process of basic clustering method, how you can arrive at particular functional modules. So here's an example. So in week 7 live session, I gave this example of a requirement where a particular product is envisioned. That is a sachet dispenser, because in a shopping mall scenario, we don't have the sachets, those 2 rupee sachets, and they have only shampoo bottles. However, if you go to small grocery shops, you get those, but those are available in a very unmanageable way. The reason, because different companies produce these sachets, and there is no standard way how those can be stored. They come with different shapes and sizes. In case of shopping malls, it is hard to manage them, so they do not keep it, and also it is hard to build them also. If individual sachets have a barcode, it is very difficult to sell them at a mall scenario. So the idea is to come up with a sachet dispenser where there will be there will be sachets of different companies, and a user use some interface and give a command that, okay, I need 5 6 sachets of this particular brand, then it will dispense it. So if this is a particular requirement, then how will you group these product functions into multiple modules? Okay, using the basic clustering method. Okay, so this was what we discussed in the live session 7, like how a flow model can be created for a sachet dispenser. So we have electrical energy and human energy as input energy. Then as a material we have sachets, and then as a signal we have the user commands like on off, or define sachet requirements, or starting a process. Okay, so all those are three types of input flows that we are supplying to this particular black box. And then as an output, what we are getting are like sound. As energy, sound, we are getting heat. Then as an outcome also we get a particular number of sessions, and as a signal we are getting some sort of confirmation signal. And what we did there, we just try to create various functions, okay, functional sub functions in between. Okay, so that is the first step. So the first step is to create a function structure. Okay, so after the functional flow model, we end up having something like this: a sachet dispenser having four critical function part. One is storing sachets, then arranging sachet, then get correct number, then dispensing sachet, feed sachet, activate roller. These are the four parallel critical function paths that we end up creating after coming up with this particular flow model. Okay, so this is what is required as a step 1 in basic clustering method. Step 2 is clustering the elements into module and chunks. Okay, so what we considered here we consider how these functional blocks. Okay, this is not a tree structure. See, there are interconnections between different functional blocks.
Yeah.
So this is not a tree structure, but next step is we need to group them into particular sub functions depending upon how they share energy, how they share material, and how they share information. Okay, now one more functional critical part could be the 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 part where electrical energy of 220 voltage is converted into some rectifier, and then it's converted into DC 12 volt. Okay, something like that. 12 volt DC, and then fed to transmit to various. So transmit. Okay, so this transmit thing actually goes to cutting sese critical functional block, detecting sese functional block. It will go to dispensing sese as well as storing sese also. Okay, storing sese it will not go, sorry. So one important criteria is that whenever we have some sort of shared functionalities which is common to various functional blocks, we take those as a module. So this is one module. Okay, so this is module one. Next we see flow of energy. Okay, next we see how core units are considering different energy inputs. Okay, so they are sharing same energy. They are sharing 12 volt here, 12 volt here, 12 volt here. Okay, and they are sharing material. Okay, one is, all are taking sachets. This is for dispensing, this is for detecting, and this is for cutting. Okay, similarly signal also can be one unit separate if it is a microcontroller unit which also need a power 12 volt DC. Okay, again this signal is provided to dispense SA, signal is provided to detect SA, signal is provided to cut SA. So because these three blocks share these energy material info, those can be clubbed into individual functional blocks. Got it?
Yeah.
And also because not only because of sharing, they also have they have different functions. Okay, otherwise those will not be modular architecture. It will be more like a what was that uh, the integral architecture, sorry. So if they have a single function, then that would be a integral architecture. But since those three functional blocks have three different functions and they are handling the similar materials, so this can be actually considered as a linear path where a sachet actually first entered. Okay, sachets are first stored in a storage sections. Okay, from there it got dispensed. Okay, okay, get correct now. Okay, from here it actually got input signal Okay, then it activates the roller, the machine inside, it activates the roller, it fed this SA and it dispense. Then what happened? Once it is dispensed, it can go on dispensing, right? So it needs to detect. Okay, so for detect, it first detects the rolling function, then it activates the sensor and it detects SAs. So it detects the particular number of SAs. Once it detects the SAs, takes this as sensor information, activate the cutting mechanism, and then it cuts the SAs. So this is more like a linear process. However, this linear process have four distinct functional blocks. Okay, that's why they are they can be considered or grouped together as four individual modules or functional blocks. Understood?
Yeah, fine.
So next is like after that, okay, after that you create rough geometric layout. Okay, so basically after that you come up with some sort of geometrical layout. So this is the dispensing system, this is the detection system, this is the cutting mechanism. Next is you need to think how this will be connected. So in this particular design, this sachet is actually, this sachet edge is fed into this dispensing mechanism. Okay, and this dispensing mechanism has a roller and it rolls. This roller section actually comes, okay, here, and it dispense the sachets through this particular sensor network. Okay, there are sensors here, and it actually detects a particular number of sachets, and when it detects the user defined number of sachets, then it activates the cutting mechanism which will actually cut the particular sachets, and that's how you get the sachets. So this is how this particular assembly is created using these four modules. Got it? So this
Yeah.
is three. Then okay, so basically stage 4 is one thing like whenever you need to check for the interactions, okay, and you need to check if there are exchange of energy, exchange of material, or exchange of information. Then if there are any some sort of disturbances, you need to make sure you take proper measure for that. So in this particular case there are no such requirements where I need to check for I need to avoid flow of material from one unit to another, or I need to avoid flow of energy from one unit to another. So those the consideration I did not have to do. So this is how we come up with product modules. The another method for grouping functions to create product modules is known as module heuristic method. So in module heuristic method, what we do here, we use some sort of heuristics. So very first step is same, we create function structure. Okay, similar to the last example, we create function structure, and then what we do, we try to use certain heuristics. So there are mainly three heuristics. One is dominant flow. So basically you find the dominant flow. So if you go if you, for example, energy is converted into some sort of output energy. Okay, so there is some sort of dominant path, critical function path. There can be sub path, for example, converting particular uh, you know part of energy into some other blocks, but those are not dominant flow path. So this dominant flow path you generally consider as one module. Similarly, there can be branching flow. So you next is you identify branching flow. So if there are some sort of branching happening, okay, in order to again end up having some sort of output, not only for energy, it can be for material also. for material also, if there's a dominant path, okay, and there can be some sort of sub path also, okay, which also can end up having some sort of material output. Okay, so these sub paths are called branching flows. Okay, so those also can be grouped, okay, as a module, okay, particular functional blocks. Then we consider conversion and transmission. So basically, whenever there is a conversion of energy, conversion of energy, or conversion of material, or conversion of information. So this is E, this is M, and this is your I or signal. So in those cases also we can consider them as modules. For example, here when 220 volt is the energy output and we have a rectifier circuit, then we come up with 12 volt, and then we have some sort of regulator, okay, 12 volt. So these, because this is a conversion of 220 electrical AC voltage to 12 volt, we can consider this particular as one module unit also. Okay. Similarly, conversion of material. For example, in certain scenario where you fed particular material and material change its property. For example, you gave a solid material and you convert into something like a powder. Okay, powder material. So that particular section which actually convert a solid material to a powder material can be converted as a separate module. For example, the mixie grinder, the top part. So this is the section where basically a solid food material can be converted into some sort of you know, powder form. Okay, so there you can consider this is as one module unit. Similarly, flow of information. So for example, if user input is given as a in a button interface, tactile button, and this button interface goes into a some sort of microcontroller. This microcontroller then send this signal to some sort of probably a stepper motor. Okay. So the flow of information which is from tactile tactile button to some sort of electrical signal, this information block can be considered as a single module. So basically these are various strategies, how you can break down a product function structure into individual modules. You don't actually have to choose a particular module blindly. You need to make a conscious decision like which will be the best module. uh, okay, there can be some sort of overlap also which you need to eliminate. For example, here you can see when I say dominant flow, the dominant flow as well as the conversion transmission of energy overlaps. So in those cases we consider you can choose either this as a module or you can consider the entire thing as one module. Okay. Clear?
Yeah, yeah.
Okay. So in the same example, I took the same example. So this is the same example where we created a flow model and we end up having a function structure. Okay. So this heuristic method is very simple. If we have created a detailed function structure, we first look for dominant flow, and there is no dominant flow in this particular case. And there are dominant flow means you need to have one particular flow. Okay. So in case of dominant flow, it will be more like this, and sub functions will be like this. But in this particular case we have four branching flows, because from the top node we have four branching nodes, okay, coming out of the main overall function which is SI dispensing. So because of that we can use the straightforward the heuristic, which is the branching flow, and we can consider these four as four individual blocks. Okay, then we can consider the flow of energy, flow of transmission, like this thing, conversion and transmission. For that, if you consider conversation and transmission, we can also consider the one more module, which is how 220 voltage is converted into, then through a rectifier it's got converted into a 12 volt DC, then a regulator provide you the regulated voltage. Okay, so this entire thing can be a module which actually provide voltage to all the three sub functions, sub modules. Okay, so this is how actually the heuristic method is useful in creating function. So any doubt here?
No, the arrow shows the downwards, but when I look into the function,
Actually, when this is created initially, it was created like this, right? As a function. So what we do generally when we create a critical function path, we break down higher function into smaller sub functions. Okay, but actually things happen from smaller sub functions to higher sub functions. So this is how actually we break down the storage of sessions. For example, the ultimate goal is storing sessions. Okay, so for that we need to arrange sessions. So this is a so arrow, downward arrow showing a functional decomposition process. So what we do in function structure, we do functional decomposition, right?
yeah, yeah,
Functional
okay.
decomposition means breaking down higher level function into smaller level. However, in reality things happen in the opposite direction. Actually,
Mm.
we first get the correct number, right? Like for example,
Yeah,
we essays, then arrange these essays, then we store.
correct.
Similarly, after storage, we
It
activate the
will
roller, then feed these essays, then dispense. After dispense, detect rolling, activate sensor, then detect essays. Then get sensor information, activate, then cut. Okay. So the downward blue arrow demonstrate the functional decomposition process. However, the way it executes is denoted by the red arrow.
yeah, clear. Thank you.
Okay, so that's the end of today's class.
Okay.
Now I can say four functional blocks. Okay, so these are four main functional branching. Using the heuristics, we come up with four. We identify four, branching flows, and in addition to that, we can also use the transmission conversion transmission heuristic. And there is actually a power unit where a 12 volt supply line goes and it supplies a 12 volt DC output. So this particular electrical unit is also a separate functional model using that conversion and transmission heuristics. Okay.
Okay. Thank you. Thank you so
Okay.
much.
Thank you for attending the class. So hope this is useful.
Yeah, this is very much useful. Thank you.
Okay.
Good.
So the deadline for the assignment is tomorrow, 28 September. So if you have not finished yet, please go through the assignments. It will be easy. After attending today's class, it will be quite easy. Those are only objective type questions.
Oh,
And the next class will be again on next Tuesday.
Tuesday. Sure, sure. Thank you.
Thank you. Bye
That's
bye.
really useful, actually. Thank you.
Bye.
Thanks. Bye.